Okay, so I'm very pleased to introduce our next speaker, Wenlu Zhu. Wenlu is a professor at the Department of Geology at University of Maryland. She received her PhD at Stony Brook University, and after her PhD, she worked at the Woods Hole Oceanographic Institution, and then moved to Maryland. So Wenlu's research focuses on the coupling between rock deformation and fluid flow in Earth's crust and the mantle. She studies evolution of mechanical and transport properties and quantifies changes in 3D rock structure at various scales. And she was the recipient of the 2020 Louis Neil Medal by the European Geosciences Union for her exceptional contributions to the understanding of coupling between fluids and rock deformation. And the title of her talk today is Recent Developments in situ rock deformation research. So Wenlu, please take it away.
Okay, thank you. Thank you for the invitation. And I'm just going to talk more about rock deformation and its presence in the beamlines. In the previous 4 talks, that there's quite a bit of covered in the more ductile field. So I am going to concentrate on the brittle field. So first, let me give you a very brief introduction about rock deformation and why it is important. Basically, Earth is a dynamic environment as well as many other planets. So one thing we are strive to understand is the dynamic process that shaped the Earth and the history of the Earth. So rock deformation is essentially this process occurs in rocks. So we need to bring them to the lab and get to know what are the physical and the chemical process behind those dynamic processes and what are the consequences so that we can get quantitative knowledge. We can do some predictions, and that is obviously important for understanding plate tectonics, earthquake physics, volcano process, and also with the more brittle field, it has a lot to do with environmental and subsurface energy resources and engineering questions and the geohazard mitigation. So what do we do? Essentially, we take rock into the lab and deform them under controlled condition. The challenge is the extrapolation is impossible. So we can never do an analog or simulation in the lab because the time scale and the spatial scale is minute compared to what happened in nature. So the way to get around it is to understand the deformation mechanism. Showing here is the picture. Here, that's the wheel, is one of the high speed friction experiments. We put rocks in between that with the high spinning. It mimics earthquake speed type of friction movement, and you will see what's going on. And on the left is actually one of the really beautiful sites in Israel where the sand and the sandstone forms this really nice wavy, like sculpture-looking mosaics. And we think that has everything to do with earthquake and liquefaction and how they move the granular flow. But these, you clearly cannot put a kilometer of rock and deform it. And you cannot also deform it for more than a few days or a few weeks, even a few years. It's hard. So what we do is almost every experimentalist had to do is after the experiment, you look at the microstructure. So we tend to isolate those pressure temperatures so that the mechanism will be singled out. You really know what produces this type of structure and then build them, piece them back together to apply to the Earth. The challenge is obvious. One thing is that pre-synchrotron, most of that microstructure is in 2D, whereas the rock and we live in the 3D world. also, even more importantly, pre-synchrotron, at least now, without the in-situ measurements, what we do is always a snapshot of the structure. It's never been the evolution of the structure. So with that in mind, maybe now it makes a little more sense what we try to do. So showing here is one example about fault propagation. You know that when fault moves, that's how earthquake gets felt if they move fast enough. So with that fault movement, the simple physics model will say, hey, that is a critical phenomena. And if we borrow from the fracture mechanics, you say, hey, if the crack grows to a critical length, then it reaches that critical state and it's become a runaway process, so there's earthquake. But once you leave it, put it into a rock, the rock has pores, has different mineral faces, and all of them actually deform differently. So what we find by looking at deform them in the rock and looking at it, showing on the right, you see the picture here, essentially shows that in rocks, most of the time, that critical length is hard to measure. It's the coalescence of those micro cracks. Obviously, with these snapshots, you don't know how these micro cracks was developed. So that's why in the early 90s, starting from pioneered by Dave Lochner in the USGS lab, they use acoustic emission. And so that's during the deformation, while the crack is developing, you can listen to it and get the, because micro cracking is essentially little micro earthquakes while the crack is propagating. By looking at the activities, you can actually see what's where the most activities are and how that's related to the overall the fracture growth that you observed afterwards. But nevertheless, this is indirect measurement, and not also we know for sure not all microcrackings generate acoustic activities. And also, if you look at the individual activities, how do they coalesce is hard to decipher. So in this talk, I'm going to show you what are the recent developments in the in-situ rock deformation in the brittle field. So this is mostly right now, given the limits and given that this limits mostly from experimentalists, we're not familiar with the beamline technology and we are just still learning the rope. So right now, the technique usually used for the brittle field is 3D microtomography combined with the deformation field. But that requires the first step is to build vessels, X-ray transparent vessels that allows you to do the experiments at the desired pressure, temperature, and stress field while measuring the pressure, temperature, stress, and strain. You also get the 3D microstructure evolution. This here is studies that recently, and I either am part of or know about, of this microtomography and how does that help us to understand the brittle field. Then I'm going to give you two examples about the dynamic microtomography, and hopefully that's these give you some idea what our need. And I'm really happy to see so many experts in the X-ray beam technologies. Maybe you can help us to see by collaboration, how can we transform this field? And lastly, I'm going to talk about an NSF-supported research coordination network. That is particularly, right now it's ongoing, and that is particularly because of the need that rock deformation experimentalists need to your help to actually develop new technology and or using existing technology to solve some of the fundamental long-standing problems. Showing here are 3 examples of the current used rigs that's particularly designed to work with X-ray so that you can deform the rock while getting the 3D microstructure evolution. So most of the time you see that they have a common characteristic. They are most of the time asymmetric, so they can rotate, so you can get the high resolution 3D microtomography. And the pressure temperature fields are slightly different. Obviously, the larger the range, the better. But sometimes we also want precise precisions about the stress and temperature control. So there's it tend to be in our pressure temperature field, it tend to be we have slightly different machines all over the place. I'm showing you here is one of those setup. It's a titanium alloy cell, and the wall thickness is about 5 millimeters. This will allow us to apply the confining pressure up to 100 MPa, axial load up to 200 MPa, and we can put, and that's important for my research, is that the upstream and downstream pore fluids pressure port, so that you can actually have flow. Fluids can be water, can be CO2, and it can be other aqueous fluids flow through the rock, so that you have the chemical and mechanical coupling. So this whole cell is, the experiment was conducted in ID19 in the ESRF. And here is the particular the beamline statistic, not statistics, numbers, type of scintillators, type of angulators, and the wigglers so that we used. This is before the ESRF upgrade. So now there's a second generation of this vessel, which now can accommodate a much bigger size. Test is done in June, and we are still looking at the data. So one of the example we did is, like at the beginning I showed you, in the lab, we do fracture of the rock, because the fracture propagation has a lot applications in earthquakes, in resources, in hydrofractings and other stuff. So we care about fracture growth. Now we can, for the first time, put in that fracture, and this is our rock, and you see the white part, that's the quartz, and the blue is it's pore space. Usually we highlight them, color them blue, because that's where the pore fluids will reside. And now we did the experiments, well, it rotates, and you can grab the 3D microtomography images while the sample deforms. And so this is what you're seeing. At the beginning, there's added axial stress, and at some point you start to see the cracks are start to grow, and these cracks follow certain regions, and you see the coalesce of it. Once it's coalesced, we measure the stress, and once the rock is completely coalesced, the fracture is thoroughgoing, the rock lost its load-bearing capacity, so now you see a sudden failure. All right, so that essentially expanded in general, the Coulomb-Moore criterion, which you all heard about, that controls the brittle fracture, and link that with every step of the microstructure deformation. So with that, the great point is now there's a lot of computing improvement and the machine learning. So now you can actually use the digital volume correlation and produce the 3D strain field. So for that the very same rock, all right, what you actually see is that the volume, you trace the volume change of a single element volume. And then you are going to see at the beginning where is a high strain and how that high strain is now coalesced, and that is a localized strain. All right, so this is also called the localization phenomena of the fracture growth. So the next step, so now you have the strain that's essentially added a dimension to what traditionally we can get with of the stress strain field. Next, it would be really nice to have the stress field. I know that's in high temperature, high pressure fields, that's you guys are measuring the stress field. We would like to see if that's possible in the brittle field, because if we, from the tomography, get to the strain field, and you help us to understand the stress field, then we are really going to understand the heterogeneity and the interactions. And that is going to be a game changer to understand how fracture nucleate and grow. Right now, I think it's still quite challenging that to get the polycrystal stress field measurement with complex geometry, but with so much talent right here, I think it's possible. You will tell me how to do it. So with that, I'm going to do another thing. So now, for years, when I started as a graduate student, I was told by my mentors that we don't do mixtures. Like, we try to really separate those processes, because if you mix everything together, you're simply creating a new problem, and that is going to be hard because it has the length scale and the time scale is so different from the Earth. It's not going to be easy to extrapolate. So what you spend all your energy about is this new system that you created. That is certainly also valuable, but that's not what Earth science is really cared about. So I actually followed that for a very long time and say, okay, we isolate those mechanisms. So when I say it's brittle fracture, it's really brittle fracture. When I look at particular grain size reduction, I know exactly whether it is brittle or it is some other plastic mechanism. Until now, because by separating it, it's going to be really hard to quantify the feedback. What if one mechanism affects the other? Once the structure changes, then the dominant mechanisms changes, right? So now it is actually start to make sense to put them back together. So we very little bit start to look at that. One of the things to look at the alteration of the rocks while deforming it is to look at mantle peridotite, because mantle peridotite is actually unstable at a low temperature with the presence of water. So serpentinization is a result of it. Because serpentine is so much less strong and with a lower friction coefficient, so that in general happens at the plate boundaries and has a lot implications in lithosphere strength, subduction bone dynamics, hydrothermal circulation, and as well as the carbon cycle that everybody talks about now. So these are the simple, we only deal with the simple chemistry right now. So this is the serpentinization, the few major reactions that you can see, the magnesium dominant olivine or magnesium peroxide that's add the water into it, so that becomes the serpentine. And then if you have CO2, they will actually call carbonized, all right? So with this, not only it has clear implications on the lithospheric strength and how the plate tectonics boundary processes. A while ago, now it's more than 30 years ago, thereabout, smart people actually proposed that, hey, this natural serpentinization and carbonation we observed can be a way to combat the carbon we released. The only thing is we need to find a way to accelerate its process. So showing here is a lot of work that's done in the 90s that's showing that this carbonation and serpentinization is actually a heat release process. And that's a heat release process make it promising because you can think that every industry that if you want to do something, you have to put energy there. So if this process is generating its own heat, you can think, hey, we can have an industrial carbonation process where it will use much less power than what's it's actually removed. One of the thing is that if you look at it, this reaction rate will be very slow unless you essentially make the peridotite grain size very, very small. But to pulverize rocks, that's very, very energy consuming, not talk about it's very expensive too. So then in the lab, we try to see how we really estimate the rate of the serpentinization and the carbonation in the natural peridotite. In a traditional ex-situ observation, you have the vessel, you put your olivine, all right, and you add your water and the CO2. What you get is you can measure the porosity during this deformation, and what we see is a porosity reduction. And afterwards, you can look at the SEM and look at what's new minerals happens and what are the previous olivine gets where, and you see lots of magnesite and so on. But that seems to indicate, this is a single crystal experiment, that seems to indicate that they are the fluid rock interaction always happens at the interface. So if then the reaction product just now precipitated at that interface, you're going to reduce the pore space, so cut off the flow. You're going to also reduce the reactive surface, so cut off the chemical reaction. So that seems to be a negative feedback unless you have extra mechanical energy to pulverize it, so your rate will be very slow. But if that's the whole picture, so there are people out there and say, wait a minute, if this is happening, then we shouldn't see fields that have 100% combination of serpentinization. What happened? That's promotes us to do these experiments at the argon advanced photon source at 2 BM. That is a DOE supported DOE supported beamline. That's we use sintered San Carlos olivine. Actually, Sean Corrado made the synthesized us for us, and these are the sample setup. And with this sample, we used what we call a hydrothermal cell. That's almost the very first generation of low pressure, low temperature, yet elevated than room pressure and temperature, but with the pore fluids flow through technique. So we can introduce carbon-rich fluids, aqueous fluids with rich carbonate in it. And then what we did was we captured a real-time 3D pore structure evolution in olivine and during its carbonation process. And this is the video showing that. So, go on. at the beginning, you see this is our synthesized ones, and in the middle, we put some big loose olivine grains, and you do see the crystal growth at the surface showing here. You see that, I'll show you next. And then what we see very surprisingly is at the end of the experiment, there are cracks growing. So what we see, if we take a look of a snapshot of 8 hours, 64 hours, and so on and so forth, up to 5 days, you see the crystal growth at the original olivine surface, and you see cracks actually in the sintered hot pressed olivine aggregates. And these are the single crystal if you take them out, and you see how the crystal grow. And then you also see that the olivine grain, which is these gray ones, was essentially eating out by during reaction dissolved into it and grow that magnesite crystals. And if afterwards that we take a electroprobe analysis, it's indeed the leftover olivine crystals and the carbon-rich, presumably magnesite or some other brucite or materials are the product. So with this, one thing that's really interesting for us is how does this chemical reaction, remember here we didn't put any stress, these chemical reactions seem to be able to drive the hot pressed olivine aggregates to crack. All right, so that's a chemical reaction driven cracks. And what we see is actually these cracks also have a pattern. They seem, if you follow this particular crystal, all right, you see that the whole sample assembly, the sample itself is expanding, and the cracks is based on our other analysis and so on. Now we propose that is actually a shrinkage crack. Is you see that in the drying mud or your baked cookies, because if the exterior is cooling and it's shrinking, then the substrate is pulling it, and that causes a crack. And what we think is that in our case, the dissolution creates that volume contrast, and then the surface cracks will allow new fluids to get enters into substrate, and that allows the chemical reaction goes on. And this is actually those crack patterns. They are very different from the brittle fracture patterns that is kind of morphologically similar to the weathering pattern of the olivine. All right, so with that, then there are also theoretical estimates how much of those chemical reaction can produce the stress. So the simple calculation without thinking about any other complication is simply the Gibbs free energy released by the crystallization now changes to pressure. So if that's a crystal growth pressure exceeds the wall strength, then you're going to break that. One of the example of a exothermic volume increase reaction you probably all have seen is if you put your champagne in the freezer, just hoping to cool it fast and forgot about it, what you get is a explosion. That's what one type of crystallization fractures. So do we have that? With the synchrotron, we designed these experiments. Essentially, we have it faster because remember, with the natural prototype, it takes 5 days. It's very hard to get beam time for 5 days. 2 p.m. They were very nice to me to allow me do that. But at any rate, So we decided that we'll get a fastest one in the analog system instead of natural peridotite. We're using periclase. So periclase MgO react with water at a slightly high temperature, which is in this case, we do somewhere around 180 to 200 C. That creates a solid volume increase of more than 100%. And this is what you see. This is a periclase with some fractures at the beginning, and with a flow through, you see how the periclase actually gets broken because the volume increase purely induced by the chemical reaction. And with that, now not only we can analyze the fracture patterns, we can also look into the porosity change and the phase change, the periclase change to brucite. So you see the continued evolution of decrease in periclase and the increase in brucite. With that, you have that volume change, and that volume change creates stress, and that actually changes create all the fractures, the increase of the porosity. So with this, we got even more daring. I said, hey, let's see if you put such a volume expanding cores, how much they can actually break the surrounding rocks. So in this case, what we, student Xiaojiao Zhang, actually, we drilled the core, and we put the periclase into the drill hole. And now we have the fluid. Outside is a serpentinized danite. All right. And from what you see before, this periclase is going to fracture and going to grow, volume growing. But if they are surrounded by rocks, all right, would they be able to crack them, or is the surrounding rocks is going to hold this together and stop the volume change? And that also has a lot of implications in this hydrofracking business. So this is what you see. This is serpentinized danite. That's our drill hole filled with the MgO core. And as your water is getting in, you start to see that there's a lot of fractures, and this fracture managed to grow and breaks the surrounding rock. And you can control the rate of the fracture grow, and by changing pressure, temperature, as well as the pore fluid pressure. So in this case, it's the same pressure and temperature, but with the pore fluid pressure, that's actually much higher. We actually see the pattern. You have a fewer, much more cracks and more uniformly distributed, and the reaction is lasting much longer. All right. So I'm running out of time, but at any rate, what I hope what I'm convincing you is that there's so much to do. We need to make the connection. Science can make a step leap if we actually are innovate, and innovation requires knowledge. If we are completely ignorant, we don't know what to do. And so that's why we have this network, rock deformation network, RCN. This is, the goal is to integrate the beamline technology with the deformation experiment, because I think for the large deformation, large portion of the deformation community, we actually are only watching you guys using the beamline technology and say, awesome. And we need you people get interested in what we do. And if we work together, we can actually identify the knowledge gaps, and we can really push a transformative science to move forward. And our RCN has a steering committee. Actually, this is on purpose. That's at least 1/3 of them are beamline technologists, and 1/3 of them are experimental rock deformation. And then we have geodynamists and structural geologists and resource people. They are all very much interested in this new technology and this new direction. We need your help, and the new organization, we would like to collaborate. And we also have a steering committee. You see that there is a lot of interest in what's the rock deformation, what we can actually quantify. So geodesic people who are looking at geodetic studies, people who are looking at earthquake physics, people who are doing geodynamics, as well as the people who look at mineral physics and rock physics. All of them, I think we have a shared interest to collaborate, to innovate, and to actually reach our goal to transform what we are doing. And that's getting new things should be exciting. And I will stop here. And my very last message is that this networking grants that we currently have, we have 2 workshops already. We had a workshop in 2020 at CHES. CHES scientists host that. And early this year, we have at APS, 6 p.m. scientists and JC Cars jointly host that. We have a couple more workshops that's planned, but there's no concrete plan. We have room for new workshops. If you have directions that you think that we should know and we should talk about, please talk to any of the steering committee member or email me. We welcome all suggestions and helps. Thank you.
All right, that was a great talk. Thank you, Wenlu. We have a few minutes for questions. Sean, please.
Oh, number one, oh, wonderful talk. Very impressive works. Okay, not plural. Great. You. And so you asked one question about the stress measurements.
Yes.
I think someone else may have a better answer, but most cases, when we measure stress in the deformation kind of environment, it's a polycrystal diffraction. So grain size might be. So in your case, probably very coarse grain size. So we must use some single crystal kind of diffraction. Someone else may have a better idea. You know, our technique is usually fine grain, like a few microns, and then you can use the like a powder diffraction theory.
If that's possible, right? We don't have to. We have fine grain rocks. Like right. Yeah, for example, Solnhofen limestone just came in mind, right? 5 micron.
Yeah.
5 micron, uniform.
Yeah, Carrara marble.
Yes, it's actually do fracture, and we don't like to use that because it's too fine grain size, and to look at the structure later is hard. But if you say synchrotron can help us, by all means, we are interested.
Okay,
you see, that's the thing.
Yeah, but
that's the thing. We need to learn from this community.
Yeah. Okay, very good. And you showed very nice experiments on the brittle field. Try to see how fracture develops. But similar apparatus you could use, like you can define pre-existing fault and then look at the friction behavior. Is that possible? I think it's possible, isn't it? Perhaps the difficulty is the velocity of friction.
Yes.
Yeah. That's I mentioned, like a equipment.
Absolutely, you're absolutely right that looking at friction is a direction that people are moving into.
Yeah, actually, when I designed RDA, I had this kind of thing in mind. So I have a big motor. So with this motor, I can go 1 meter per second.
We would love someone help us to convert that or to adapt that to be able to become a rotary shear apparatus for friction. The only thing right now for friction is that if we have events, right, those tend to be the slip event is very fast, and getting the 3D tomography can be a little, the snapshots are still, even though it's only a few seconds, but the event can be a tenth of a second or hundreds of seconds.
But overall, those studies have a tremendous impact to many, many questions. So I think it's very.
That's right, but we need to learn tremendous things from you guys before we can actually materialize this.
Well, that's why we have this kind of workshop, isn't it?
Yeah, that's right. That's
and
right.
I also think that the new organization should be when we wrote that proposal, Sean, you know that you actually wrote part of our introduction.
Sure, yeah.
So when we wrote that proposal, we clearly didn't have any idea, what synchrotron will be reorganized, on their science will be reorganized, right? So we were just hoping to learn more about the technique and to become a major force in the user community. Now I learned a little more, like yesterday when everybody already said that they don't have enough time. I'm like, oh my God, if there's already not enough time, can we make some room for the newcomers?